Hello everyone and welcome back. We are looking at geometric sequences and series today. These are similar to the arithmetic sequences, but the arithmetic sequences have a rule that is linear. The geometric sequences have a rule that's going to end up being exponential. So our goal today is to be able to identify when you're given a list, whether it's geometric or not. We're going to write rules, lots of rules that are geometric for geometric sequences, and we're going to find sums of a finite geometric series. So this lesson is very similar to the last lesson in that we're going to be doing kind of the same thing but with geometric sequences instead of arithmetic sequences. All right, so the first thing we're trying to figure out is whether or not something is a geometric sequence by looking at the list. So once again, remember, a geometric sequence, when you say sequence, it is the list that we're talking about. And when you say a series, we're talking about the sum. So the numbers that are in the series are from the sequence. So another thing I want to add to your notes here, if it's geometric, we're going to have a common ratio instead of a common difference. In the arithmetic sequences, we had a common difference that we called D. In the geometric sequences, we're going to have a common ratio that we're going to call R. And that R is going to become the base of our exponential function. So it's very similar to exponential functions. And back in chapter 5, I believe it was, we wrote equations for exponential functions, and you're going to see that writing the equations for these geometric sequences and series is going to be very much like the exponential functions. Okay, so in a geometric sequence, the ratio of any number to the previous term. So any number to the previous term is constant, which basically means it's the same. This constant ratio is called a common ratio. So whether we call it constant ratio, common ratio, they mean the same thing, and it's notated with R. So here are three examples, and we're trying to figure out whether these sequences are geometric or not. When we were trying to figure out if they were arithmetic, we subtracted, again, right to left. But instead of subtracting, we're going to divide. So ratio is like a fraction. But again, go right to left. So the 324 over the 108. And if we simplified that, it would equal 3. If we took 108 divided by 36, that would also equal 3. If we took 36 divided by 12, that would also equal 3. And 12 divided by 4 also equals 3. So we found out, yes, it is a geometric sequence. Because, so my abbreviation B/C, it has a common ratio of 3. And that's really what you have to do when all you're doing is given a list and you're trying to state whether or not, trying to figure out, is it a geometric sequence, is it not? Okay, so then we'll look at the next one. If we take, again, right to left, 25 over 30, if we reduce that, we get 5 over 6. If you take 30 divided by 35, that's going to reduce to 6 over 7. So right away we can see that they are not the same So it is not geometric because it does not have a common ratio. All right, so not geometric because it does not have a common ratio, or there's no common ratio. And then there's one more example. You probably don't need it, but you will see some things with fractions, so it's kind of nice once in a while to have a fraction example so that you're not freaking out from fractions. So once again, if we go right to left, now when you're dividing fractions, you have to multiply by the reciprocal. So if we take that, if we're dividing the 3 over 32 by the negative 3 over 16, it's going to look like this. 3 over 32, instead of dividing, we're going to multiply by the reciprocal of that second fraction, or the one before it, and I get negative 16 over 3. So then the 3's can reduce, and the 16 and the 32 can reduce, which will give me 1 and 2, or negative 1/2. So that's what we get when we take the 3 over 32 divided by the negative 3 over 16. So let's see if that negative 1/2 ends up being our common ratio for the rest of these. So I'm going to use this space above here to divide this negative 3 over 16 by the 3 over 8. And again, when you're dividing fractions, you're going to multiply by the reciprocal of the second one. So 3, or negative 3 over 16 times the reciprocal, which is 8 over 3. Again, you can see that the 3's reduce, and your 8 and your 16 also can reduce to 1 over 2, which again gives us a negative 1/2. So far, so good. Looks pretty good. If we were to check again and take our 3/8 divided by the negative 3/4, so if I'm dividing a fraction, I'm going to multiply by the reciprocal, negative 4/3. Again, you can see the same pattern happening. 3 is reducing. The 1, or the 4 and the 8 gives me 1 and 2, which again gives me negative 1/2. And if I were to do this one more time with the negative 3/4 divided by the 3/2, that would also give me negative 3/2. So we can see now that it is a geometric. So yes, it is geometric because it has a constant ratio of negative 1/2. Okay, so hopefully now you know what to do if you're asked to identify whether or not something is a geometric sequence. The next objective is for us to be able to write a rule for our geometric sequences. And just like the rule for the arithmetic sequence, this is a formula that you're going to want to highlight, and it's one that we're going to use for the next few examples. So in this formula is used to find the nth term of any geometric sequence. So if you wanted to find the 5th term or the 10th term, you would have to substitute whatever term you're trying to find in for n, but we need to know what that ratio is. That's part of our equation, and we need to know what the first term is in our sequence. So in this example here, it's just a quick example, they say that if the first term of the sequence is 2, so that would be your a sub 1, and the common ratio is 3, that would be your r, then this would be the equation. So the a sub 1 is 2 and your r is 3. So now if I wanted to find the 10th term of this sequence, I would plug in 10, take 10 minus 1, get 9, take 3 to the 9th power times 2, and would give me the output. but that's not what we're asked to do, so we are going to be writing equations or rules to go with these geometric sequences now in example 2. So the first one's a relatively easier one because we have whole numbers, and it's going to be pretty easy to divide right to left. So the negative 24 divided by 12 equals negative 2. 12 divided by negative 6 also equals negative 2. Negative 6 divided by 3 also equals negative 2. So our common ratio, R, equals negative 2. So that's one piece of the equation that we need. So here's our formula. So we need the ratio. It's kind of like the base when we were writing exponential functions. Now R is representing the base. We used to have a B here when we wrote exponential functions. Well, now they just call it R because they're calling it a ratio. But don't let the variable confuse you. It's the same thing. So it's the same as we had when we were writing exponential functions, and we put the base here. But now we're calling the base the ratio. So negative 2. How do we find, the other piece that we need is the a sub 1. So how do we find it? Well, it's the first term in the sequence. And if you look at the list, what's the first term? 3. So 3 is our a sub 1. So once we've got those two pieces, we can then write our equation or our rule. The formula, once again, a sub n equals a sub 1 times r to the n minus 1 power. Now, a lot of times I like to put the base or the ratio in parentheses, especially when it's negative. You have to actually put the negative inside the parentheses so that the negative is also being taken to the power, so that when you look at the list, the sequence, you can see that it's going from positive to negative to positive to negative. That's only going to happen if your negative is inside the parentheses. So be careful when you're writing it to use those parentheses. A sub n now will equal a sub 1, which we said was 3. R inside parentheses is negative 2, and then n minus 1. So this is your formula. Your formula, the n is the input, so it's kind of like your x when you plug it in, and then a sub n is the output. So now that we have the equation, the next thing they're asking us to do in our directions, it says write a rule for the nth term of a sequence, which we just did, then find a sub 6. So they want us to find the 6th term now in the sequence. So that's not going to be too hard. Since we know our rule, we just have to say a sub 6 then is going to equal 3 times negative 2 to the 6 minus 1 power. And 6 minus 1 is 5, so 3 times negative 2 to the 5th power. Don't forget to use your order of operations. You have to take the negative 2 to the 5th power first, then multiply by 3. So a sub 6 equals 3 times negative 2 to the 5th power is negative 32. Let me think here. Yes, negative 32. And when I multiply that together, it gives me negative 96. So negative 96 is the 6th term in the sequence. So a sub 6 equals negative 96. So we completed the instructions, which were to write a rule, which we did here by finding our ratio, plugging in our first term for a sub 1 and r, and then we found a sub 6 by putting 6 into the rule for n. Great, so moving on. Example B. This one is just a little bit more difficult because it's fractions, but again, don't let the fractions scare you. You just do the same steps that we did before. We're going to divide right to left, right to left, right to left. So if I took the 125 over 8 divided by the 25/4, dividing a fraction is the same as multiplying by its reciprocal. So I'm going to do this over here. 125 over 8 divided by 25/4 will be the same as multiplying by 4 over 25. and then we can reduce the 125 and 5. Both can be divided by 25. So when I divide that by 25, think quarters. How many quarters in $1.25? 5. How many quarters from a quarter? 1. And then these two we can divide by 4, which gives us 1 and 2. Multiply across, and we get a ratio of 5/2. Okay, so that's what we got when we divided the 125/8 by the 25/4. So let's see if we get the same thing when we divide the next two, the 25/4 by the 5/2. So I'll do that right here, 25/4. Why am I writing R? Okay, 25/4 divided by, which instead of division, I'm going to multiply by the reciprocal, 2/5, and then reduce. So once again, the 25 and the 5 can be reduced, which gives us 5 and 1. The 2/4 we can reduce to get 1 and 2, multiply across, and again we get 5/2. So I'm pretty confident that my ratio is going to be 5/2. And if you look at the last one here, 5/2 divided by 1, well, anything divided by 1 is itself. So 5/2 divided by 1 is just going to equal 5/2. So we do have a common ratio. We do have a geometric sequence. So now we're going to write the rule. So we know that R equals 5/2. We're pretty confident with that. And in order to write the rule, we also need not only the R, or the base in our equation, but the a sub 1, which is the first term in the sequence. So if we look at our list, the first number in the list is 1. So that's my a sub 1. So now that I know my a sub 1 and my R, I can then write my equation. Once again, the formula, the more you write down the formula, the easier it is to remember. A sub n equals a sub 1 times R to the n minus 1 power. So again, we're writing the rule for the nth term. So the n is part of your equation. We need to substitute a number for a sub 1, which in this case is just 1. Our ratio is 5/2. And then again, the n is part of our formula. Now, the only thing that's not necessary here, since your a sub 1 is just 1, we don't really need to have that there, so we can simplify this a little bit to a sub n equals 5/2 to the n minus 1 power. So there we have our rule. And then you could probably find the sixth term. It says then find a sub 6, so the sixth term of the sequence. A sub 6 equals 5/2 to the 6 minus 1 power. When I subtract 6 minus 1, I'm going to get 5/2 to the 5th power. And if I simplify, I'm going to have to take 5 to the 5th power over 2 to the 5th power. So a minute ago we said that 2 to the 5th power was 32. Well, what about 5 to the 5th power? So if you use your calculator to figure out what 5 to the 5th power is, you get 3,125, and then 2 to the 5th power is 32. So the sixth term in this sequence would be 3,125 over 32. All right, so there you have it. That's how you write a rule when you are given a list. So once again, we were given a list that was a geometric sequence, and we wrote the rule for that geometric sequence, and then we found the sixth term. All right, so hopefully everyone got that. We're going on now to the next example, which again is very similar to what we had done with the arithmetic sequences, where you were given, you are writing a rule, but the information that you're being given is a little bit different. We have, instead of being given a list, we are given one of the terms. So we're told the 8th term in the sequence is 384, and the ratio is 2. But we can't write our equation until we know the first term. So we're going to use our formula. I want to move over to the left. So, well, okay, I guess we'll start here on the right and then move to the left. So our formula, a sub n equals a sub 1 times r to the n minus 1 power. All right, so now where do we plug things in? We don't know a sub 1, but we are going to use 8 for our n. So n is 8. So if we say a sub n, or a sub 8, is going to be 384. So the 384 is going to take the place of the a sub n in our equation. But the n value is 8, which means we're going to put 8 over here. And then the 2 is going to go in place of r. So this is what's going to look like. Instead of a sub n, we're going to use 384. A sub 1 we don't know. R is 2. N is the 8 that we were given, because we're given the 8th term. So now it's a matter of simplifying and solving for a1, a sub 1. So 8 minus 1 will give us 2 to the 7th power. Bring down the rest, and then figure out what 2 to the 7th power is. If you don't know that off the top of your head, use your calculator. 2 to the 7th power is actually 128. And then to solve for your a sub 1, just divide now by the 128, and we get a sub 1 is equal to 3. So now we've got our first term. And again, what do we need to write the equation? The first term and the common ratio. So we've got both pieces of information that we need. So now I'm going to move it over here. Again, I'm going to use that formula, a sub 1, or a sub n equals a sub 1 times r to the n minus 1 power. Since we're writing a rule for the nth term, the n now is part of our equation. That is our input. A sub 1 now I know is 3, so I can substitute 3 there for my a sub 1. My common ratio is 2, and then n minus 1. Be careful that you do not multiply the 3 and the 2 together. I've seen that mistake being made by some students. You cannot multiply those together until you take 2 to a power, because your exponents, order of operations, exponents come before multiplication. So if you don't know what your exponent is, you cannot do anything else. So there we have it. That is the rule to find the nth term of this sequence that has an 8th term at 384 and a ratio of 2, common ratio of 2. Okay, good. Hopefully you understood that. If not, go back and review it again. Oh, and I do have one more example. Great. Like I've said before, I like to give 2 examples of every type of problem so that if you didn't understand it the first time, hopefully you'll understand it the second time around. So we're doing the same thing, same process, but we're given the fifth term in the sequence, which is 32, and our ratio, instead of being a nice pretty whole number, is a fraction. We are also going to graph the first 6 terms of the sequence. So there's a little bit more to this one. When you are graphing, though, remember this is not a continuous function. So the points are just there are going to be 6 points on the graph, and they are not connected. Okay, so writing the rule. As before, the rule for a sub n equals a sub 1 times r to the n minus 1 power. We don't know a sub n, or we don't know a sub 1, but we're going to use this term temporarily. So your n is going to equal 5. 32 is your a sub n, or in this case a sub 5, and then the ratio is going to be put right there for r. So instead of a sub n, we're going to use 32. A sub 1, we don't know. Our ratio is 2/3. And then now in place of n, we're using 5 because it's the 5th term. But the 5th term is equal to 32. So that's why 32 goes here and 5 goes there. 5 minus 1 will equal 4. So a sub 1, whatever it equals, times the 2/3 to the 4th power has to equal 32. Take your 2/3 to the 4th power so we can distribute the exponent to both the numerator and denominator. So 2 to the 4th power is 16. 3 to the 4th power is 81. So a sub 1 times the 16 over 81 has to equal 32. Well, at this point, we would normally divide by this number, but since it's a fraction, multiplying by its reciprocal would make more sense. So if I multiply by the reciprocal, 81 over 16, and I multiply by the reciprocal 81 over 16 here also, that's going to eliminate that fraction, or reduce that fraction on the right, but I do need to simplify this fraction on the left. You can make the 32 a fraction by putting it over 1, and then reduce the 32 with the 16, because that's in the numerator, that's in the denominator. They both can be divided by 16, or another way of saying that is they both have a factor of 16. So if I divide this by 16, I will get 2. If I reduce this by 16, I get 1. And then multiply across the top. 81 times 2 is 162 over 1. So a is going to equal 100. A sub 1 is going to equal 162, which means the first term in our sequence is 162. And we're going to have to graph that also in a minute. Okay, so what all do we have to do? Our directions tell us to write a rule for the nth term of the geometric sequence. So now that we know what the first term is, and we know what the ratio is, we can actually write the rule. Again, that rule, in case you forgot, a sub n equals a sub 1 times r to the n minus 1. Since we're writing a rule for the nth term, the n now is part of our equation. But now we can substitute 162 for a sub 1. We can substitute the 2/3 for our base, which is called a ratio, common ratio. And then again, n is part of the equation, n minus 1. So this now is our equation or rule for the nth term of our sequence. All right, well, now that we have that, they then asked us to graph the first 6 terms of the sequence. So I'm going to actually make a table so that we can kind of see the points and how they evolve. So n is the input, a sub n is the output. We need to find 6 terms. Okay, so we're going to have to write a little bit small here. The first term we already know is going to be 162. So when n is 1, a sub n is 162. So always use the information you've already found. Now we have to substitute 2. So over here, I'm going to do the work. 162 times 2/3 to the 2 minus 1 power. So I'm substituting 2 for n. Well, 2 minus 1 is just 1. So basically it's 162 times 2/3 to the first power, which is itself. So then if you take 162 times 2/3, I could probably do this without a calculator, but if you want, use your calculator. Take 162 times 2ABC3, use that fraction button, and that will simplify to 108. So that's our second point that we're going to graph. The third point, now we substitute 3, 4, 5, and 6. So I'm going to go through the substitution process a little bit quicker. I think you can see how to substitute, or you should understand that by now. The 162 is, again, our a sub 1, 2/3, but now we're substituting 3 for n. So 3 minus 1 will give us 162 times 2/3 squared, because 3 minus 1 is 2. Simplify, you always have to do the exponents before you multiply. So if I take 2/3 to the second power, that will give me 162 times 4/9. And you could plug this in the calculator, just 162 times 2/3 squared. Or you can simplify the 2/3 to 4/9 and then multiply. Either way, you're going to get 72. All right, well, at this point, we don't really have to. There is a little bit of a, you can hopefully see that there's a little bit of a pattern going on here. And if you understand what's really happening, we're multiplying. If you look at what's happening, we're taking 162 times 2/3 to the first, then 162 times 2/3 squared, which basically means we're multiplying by 2/3 again. So we could, at this point, just take 72 times 2/3, and that would give us the next number in our sequence. If you don't understand that, you can always go back to plugging in 4 for n, and then subtracting 1 to get 3, take 2/3 to the third power, times your 162. But if you understand that the next number in the sequence is going to be 2/3 of the previous one. So 2/3 of 162 is 108. 2/3 of 108 is 72. So if I take 72 times 2/3, that will give me 48, which will be the next number in the sequence. And let me kind of separate this a little bit here so that my numbers aren't all running into each other. And that'll make it easier to find the fourth term, the fifth term, and the sixth term. So now I'm going to take 48 times 2/3. So again, the next number in the sequence is going to be 2/3 of the previous one. 2/3 of 48, if I work that out, would be 32. And then for my last term, if I take 2/3 of 32, that will equal 21 1/3. Now I'm ready to graph. I've got all my numbers, all my terms, or all my points there, but remember, this is not a continuous function. It does not have a y-intercept. The starting value is 1, which means our smallest x value or input value or domain value is 1, and there are no values in between. It's 1, 2, 3, 4, 5, and 6. Those are the input values. These are the output values, and there's nothing in between those points. Okay, so look at the intervals carefully. This is supposed to be 100. Let me see if I can squeeze it. That's supposed to be 161, or 160, 140, 120, 100, and then 80, 60, 40, 20. So if I'm graphing the point 1, so these are going up by 20s. These are, the horizontal axis is going by 1s. So graphing 1 and then 162 is going to put my point approximately right there, just a little bit above the 160 line. Then graph 2 and 108, which is about right there. and then 372, which if this is 60 and this is 80, then 70 is about halfway, so 72 is maybe a touch above halfway. 448, so 448, again, if this is 60 and 40, then 50 is halfway between, but it's going to be a little bit less than 50. 532, 532 is going to be about right there, and then 6 and 21 1/3 would be about right there. So if this was connected, hopefully you can see kind of the curve there, and it would be an exponential function if this was a continuous function and if it was just y equals rather than a sub n equals. So if it wasn't a sequence or a series, then we could connect the points and it would have that horizontal asymptote at the x-axis and a vertical, or well, no, it wouldn't have a vertical, but it would keep going up to the left slightly. So there we have it. There's the first 6 terms of our sequence, and we wrote the rule. Example 4. In these examples now, you are not given your ratio. You're not told what that common ratio is. So we have to find both the first term and the common ratio using 2 values or 2 numbers that they've given us in the sequence. So what they're telling us is the third term in the sequence is 20. The 6th term in the sequence is negative 160. So from that information, we basically have 2 points where 3 is our input, 20 is our output. 6 is our input, negative 160 is our output. If this was an arithmetic sequence, we could use our slope formula to find the common difference. But this is not an arithmetic sequence, it's a geometric sequence. So we are going to use that same formula that we've been using to write our rules, which again is a sub n equals a sub 1 times r to the n minus 1 power. So we're going to substitute 3 for n and 20 for a sub n. And we're going to do that for this point and that point. And as we go through this, you're going to hopefully recognize how the similarities between this and writing exponential functions. Okay, so here we go. So here's my formula. A sub n, I'm going to substitute with 20. A sub 1, we don't know. R, we don't know. But my n is 3. So 3 minus 1 is going to equal 2. So I have 20 equals a sub 1 times r to the 2nd power. So that's really as far as I can go until I have another equation. If you have 2 variables, you need 2 equations to solve for those variables. So my second equation now, again, I'm going to use a sub n equals a sub 1 times r to the n minus 1. But the negative 160 is going to go in the place of my a sub n, and the 6 is n. So here we go. Take that negative 160 and put it in the place of a sub n. A sub 1 we do not know, r we do not know, but we're going to use 6 now for n. So negative 160 is the 6th term of the sequence. So your n is 6, but the a sub n, or the output, is negative 160. If I simplify this now, I have negative 160 equals a sub n times r to the 5th power. So we have now our 2 equations with our 2 variables. So what you need to do now is solve one of the equations for one of the variables, and then we're going to substitute it into the other equation. We did this again before with exponential functions. I like to use the one with the smaller exponent. I just think it makes it a little easier. So if I divide by r squared on both sides, and I flip it around, I would have a sub 1 equals 20 over r squared. which you could also, and I was thinking about this with exponential functions, you could also write that as 20r to the negative 2 power if you wanted, because that 2r to the second power, if I moved it up, would make it a negative exponent. That may make it easier to substitute. So where are we going to substitute this? We're going to substitute it into the other equation for a sub 1, because this is saying a sub 1 equals 20r to the negative 2 power. So if I substitute it in that second equation, I'll have negative 160 equals, I'm going to take the a sub 1 out, put 20r to the negative 2 power in its place. So this is now all from the a sub 1. I don't like the look of that 0. So the 20r to the negative second power goes in the place of a sub 1. And then I have this times r to the fifth. So hopefully you can see now why I made that r to the negative 2. When you're multiplying things with the same base, you add the exponents. So if I'm adding the negative 2 and the 5 together, I'm going to get r to the third. But the 20 will be in front of it, so I now have negative 160 equals 20 r to the third power. All right, so we have to solve for r. We're almost done. We're getting there. Divide by 20 on both sides. Negative 160 divided by 20 is negative 8. And then take the cubed root of both sides of the equation. What color do I want to use? I'm going to use pink, I guess. Take the cubed root of both sides of the equation. Because it's an odd root, there's only one root. If it was an even root, then we would have 2 roots. And that does, I think, complicate things a little bit. The cubed root of negative 8 is negative 2. Great, so now we have our r, and what else do we need? Well, we're writing an equation for the nth rule. We need the a sub 1. So now we can take that negative 2, which we just found as our ratio, and do full circle, plug it back in there for r to find a sub 1. So here's our equation. A sub 1 equals 20r to the negative 2 power. We just found r, so we're going to substitute that r in for, or that negative 2 in place of r. So a sub 1 is equal to 20, and then the r is negative 2 to the negative 2 power. Now it's a matter of simplifying this. We don't necessarily want to, you could put this in the calculator, but we're going to try to do it without. Take your negative 2 to the negative 2 power. I'm going to move it down to the denominator so that I'll have 20 over negative 2 squared. So I could have just plugged it in, the negative 2 in there right here, and would have been in the denominator already. But either way, we're going to still get the same a sub 1 value. So we're going to now have 20 over negative 2 squared, which is will be a positive 4. 20 divided by 4 will equal 5. So we have our a sub 1 and our r. Now we can write our equation. So let's just put that right over here. A sub n. So n now comes back into our equation. It's part of our rule. A sub 1, which is 5, times r, which is negative 2, to the n minus 1 power. Finally, we have our equation. So just review again, what did we start with? We started with 2 numbers in the sequence. So we were told the third number was 20, the sixth number was negative 160. we used our formula a sub n equals a sub 1 r to the n minus 1. We substituted 3 for n, 20 for a sub n, and we substituted 6 for n and negative 160 for a sub n in two different equations. Take the first equation, or either one of these really, and solve for a sub 1. Once you've gotten that, you plug that into, or that expression into the a sub 1 into the other equation. Simplify that to solve for your radius, or not radius, your ratio. Then take that negative 2 that we found and plug it in either here or over here so that we can find a sub 1. So I had plugged it in here, negative 2 to the negative 2 power. I rewrote that by putting it on the bottom, making my exponent positive. The negative 2 squared is 4, 20 divided by 4 is 5, and then I was able to write my rule for the nth term. So there's a lot of steps involved in that one, but you can do this. Just focus on one step at a time. And just to make sure that we have some good practice or enough examples that you're able to do it on your own, here's a second example. All right, so n now is going to equal 2. Our a sub n is going to be negative 48. So our formula a sub n equals a sub 1 r to the n minus 1 power. A sub n, I'm going to use the negative 48. A sub 1 I do not know. R we do not know, but my n is 2. So if I take 2 minus 1 in my exponent, I'm going to get 1. So negative 48 equals a sub 1 times r to the first power. And this would probably be the easiest one to substitute or to solve for a sub 1. So I'm going to go ahead and do that right now. If I just divide by r on both sides of the equation, I get a sub 1 equals negative 48 over r, which you could also rewrite as negative 48. That's not what I meant to do. All right, let me back up here. Negative 48 r to the negative first power, if you wanted to make it a single expression. But I can't plug that in until I've used my 5 and the 3/4. Again, my formula a sub n equals a sub 1 times r to the n minus 1. But the 3/4 is what I'm going to substitute for my a sub 1, or a sub n. The 5 is going to be my n. So plugging those values in, I get 3/4 equals a sub 1 times r to the 5 minus 1 power, or 3/4 equals, and then at this point I've already got my expression for a sub 1, so I can substitute that in right in this step here. Negative 48 r to the negative first power times r, and then if I subtract the 5 minus 1, that's going to give me r to the 4th power. So at this point, I can add my exponents. Now I have 3/4 equals negative 48 r to the 3rd power. So I'm going to divide now by the negative 48. And you're thinking, uh-oh, I have to divide a fraction. Well, you can either plug it in a fraction calculator or you could multiply by the reciprocal. So let me write that over here. It's right below. 3/4 times the reciprocal of negative 48 would be 1 over negative 48. I can then reduce the 3 and the 48, because 48 can be divided by 3, which is negative 16. So then if I multiply across, I get 1 over negative 64 will equal r to the 3rd. So working with fractions is a little bit more complicated, but just follow the same steps, and if you have that fraction calculator, use it. So at this point now, again, we have to take the cubed root of r, Since it's a cubed root, we've only got one root. So that gives us r, which will equal the cubed root of 1 is 1. The cubed root of negative 64 is negative 4. So r is basically negative 1/4. So now that we know r, we can then find a sub 1 by plugging our r in here, or here. So if we think about this, r to the negative first power means the inverse or the reciprocal of r. So if I know that r equals negative 1/4, then r to the negative first power is going to equal negative 4. So I could just substitute negative 4 in for the r to the negative first power. So sometimes you have to be a little creative with your mathematics and simplifying things. And let's separate this area here. This formula here is going to be a really important one when we're finding the sums in the next example. So now I'm going to multiply the negative 48 and the negative 4. They're both negative, so that's going to give me a positive 192. So don't forget we are using the r, which is negative 1/4, for our equation, or our rule formula that we're going to write in a minute, and a sub 1. But we have both pieces of the puzzle now, so we can put it together. I'm going to go back up and find some room over here. So my a sub n, my rule for my nth term, I guess I'm going to have to zoom out of that a little bit. The rule for my nth term is a sub 1, which is 192, times r, which is negative 1/4, to the n minus 1 power. And there you have your rule. All right, one more concept and two more examples, a and a b example, and then we're done with this lesson. So just like with arithmetic sequences, we are going to be finding a sum, but we're finding the sum of a geometric sequence. So here's our formula. The sum of the first n terms of a geometric sequence can be found by multiplying the first term of the sequence times this expression here, which is 1 minus your ratio to the nth power over 1 minus r. So over here we have our first example. In order to, and what this is saying is find the sum of the first 8 terms. So this upper limit tells us how many terms are in our sequence. That also tells us n. So n is going to equal 8. So we know what to plug in for n here and here. We need to figure out what the first term of our sequence is. So if we substitute 1 into our rule, we just get 1 minus 1, or 0, and anything to the 0 power equals 1. Now you can also kind of just look at this rule here. We could rewrite this rule as k equals 1 to 8. Since there isn't a number in front of our base that's being multiplied, we could multiply or rewrite this as 1 times 5 to the k minus 1 power. So within this rule, you can really see what your r is going to equal. And you can see what your a sub 1 is going to equal. And your n is your upper limit. So there really isn't a whole lot of calculations to work out here. You just have to know how to recognize the pieces that we need to substitute into our formula. So the 5 is going to be our r, the 1 is going to be a sub 1, and 8 is n. Okay, so our formula, S sub n, and n again is 8. So here we go. S, or the sum of the first 8 terms, is going to equal a sub 1, which we said was 1, times this expression here, 1 minus r, which is 5, to the nth power, which is 8, divided by 1 minus r, and r again is 5, so you use that 5 twice. Now it's a matter of simplifying this. Well, since you're taking 5 to the 8th power, I would suggest you use a calculator. Since you're multiplying by 1, we really don't need to bring down that 1. So 1 minus 5 to the 8th power okay, I'm just looking at my notes here from last year. It looks like I just kind of plugged the whole thing in the calculator. So 1 minus 5 to the 8th power is going to equal negative 390,624. So negative 390,624. In my denominator, the 1 minus 5 equals negative 4. So now I'm going to divide that value by negative 4. You probably could put the whole thing in the calculator at one time, but make sure you hit equals before you divide by the negative 4, or else you're going to get an incorrect value. So now I can write my answer. The sum of the first 8 terms is going to equal, when I divide this, 97,656. So some of these are going to be big numbers because it is an exponential function. So as we take numbers to the 8th power, the 6th power, 7th power, you're going to get some large numbers in here. So don't let the large numbers make you think you did something wrong. Just double check your calculations and it'll be correct. All right, so one more example and then we're going to be done. Okay, one note that I just was looking at here, the sum of the first n terms of a geometric sequence with a common ratio of r not equaling 1. Just like with exponential equations, your base or your ratio cannot equal 1, because if you take 1 to a power, it's always going to equal 1. So there really is no growth or decay when your base is 1. It also cannot be 0. So your r here cannot equal 1, it cannot equal 0. Okay, so in this next example, if we look at the notation, the 7 here tells us the value for n. The negative 16 is the a sub 1. The 0.5 is the value for r. So you can see all of those pieces that we need right from our equation, or the summation notation. But to find the sum, we're going to use this formula again. So the sum of the first 7 terms is going to equal the first term, which was negative 16. And if you're not confident that is the first term, just put 1 in for t minus, or I think that's supposed to be I. Yeah, that's a I. So I, which is 1, if we substitute 1, 1 minus 1 would be 0. Anything to the 0 power is equal to 1 times the negative 16 is going to equal negative 16. Now we have to plug it into the rest of this formula. So 1 minus, our r is the 0.5 to the nth power, which is 7, divided by 1 minus r, which is again 0.5. Now it's a matter of calculating. Now when you take a value like 0.5, which is between 0 and 1, to a power, that's going to give you a smaller value where your number that's bigger than 1 to the 8th power is going to give you a very big number. So we're going to have to use a calculator with this one. And I think I'm going to grab a calculator and kind of show you how to plug it in. All right, so I want to calculate this separately and then multiply it by the negative 16. So in my parentheses, I want to do a separate parentheses for the numerator and the denominator. So I'm going to put parentheses around the 1 minus 0.5 to the 7th power, and then I have to put another set of parentheses around, or you can calculate this on your own. 1 minus 0.5 is going to equal 0.5. So that's a calculation you can kind of do in your head, which might make it easier to plug in the calculator. All right, so I'm going to start with this, the 1 minus the 0.5, or just 0.5. Do not close the parentheses yet. You want to make sure you're taking the 0.5 to the 7th power, not this whole thing to the 7th power. So caret 7, then close the parentheses. So you're taking 1 minus the 0.5 to the 7th power divided by the 0.5, or just 0.5. Then I'm going to hit my equals. So I'm going to keep that in my calculator and then multiply it by the negative 16. That's an easier number to write down. So we want exact values if at all possible. So use your calculator to get exact values. So negative 31.75. So that is the sum of the first 7 numbers of this geometric sequence. And that's the end of our notes for today. Thank you for listening.